Hello friends, welcome to our channel Physics for You. And yes, today in this video we are going to learn about one of the practical, and that is viscosity of liquid by oscillating disk method. That means we have to find the coefficient of viscosity of that particular given liquid, whatever it may be. But for our experiment we will use the water. That means final target, final ultimate solution or final aim of our practical is what? To determine the coefficient of viscosity of the liquid. Moreover, we are using here water. So, to determine the coefficient of viscosity of water, right. So, that is our final answer. So, first of all, viscosity means we know that it is a property of any liquid, and by which we have, or the liquid itself exerts some force on the material which is passing through it, and that is what we call the viscous nature of that. That means we know the oil is more viscous than water. Again, if we go to the higher viscous material, then we can say yes, grease is also more viscous than the oil, and so on. So, those are what the viscous materials. And for some experimental use, for some industrial use also, we must know the coefficient of viscosity, how much is the ability of that particular material of having viscous nature, and that is so. Yes, what I was saying, that for some industrial purpose we require the viscosity property, and how much is the viscosity coefficient and all. So, here we will use the simple method in our laboratory, and so that we can determine the coefficient of viscosity. So, for this particular experiment, the apparatus required are oscillating disc, a stopwatch, and the liquid. Now we are using water, a lamp, and scale arrangement. In previous practical we have seen the lamp and scale arrangement also. So, an oscillating disc which is fixed to the wire, that means one end is fixed to the wire hang, and other end is fixed to the disc, so it can oscillate. That is what we call the oscillating disc. And now you can see, this is what the final formula. The formula is looks like so very longer. Yes, it is longer and little bit complicated also. So, this formula is we have to use finally to find the coefficient of viscosity. Let us first of all understand what are the each and every notation in this formula. So, eta, we know it is what the coefficient of viscosity. It is not n, it is eta. It is the notation for coefficient of viscosity. Then 16 I square, this I is what? The moment of inertia of the disc, right. Then in the denominator pi, rho is what? The density of the liquid which we are using. T is again the time period. We have to measure the time period of the disc, oscillating disc, and time period we know the time required for one oscillation. So, we will find that by our usual method. We will first of all take the 20 oscillations, and then after taking 2 or 3 trials we will take the mean, and finally we will divide that mean by 20, so that we will get the time period for one oscillation. Yes. Then here is a small r. So, that r is the radius of disc. Again, that radius we will find by finding the circumference. So, let us take a string, or yes, a small string we will take, and we will measure its circumference, and yes, by equating that circumference is equal to 2 pi r, we can find the r. Okay. Then d is what? The thickness of the disc. So, by using screw gauge we can find the thickness of the disc, right. So, this is over. Now, here it is lambda 0, pi is again constant. So, what is lambda and lambda 0? So, lambda is the logarithmic decrement in the liquid, and lambda 0 is the logarithmic decrement in air. So, what is that logarithmic decrement? We know that whenever something is oscillating, even though our simple pendulum also, so due to the air drag force, air resistive force, the oscillations are going to decay after some time. We know that those are called as damped oscillations, we have seen in second year. So, those damped oscillations, or due to this damping, the oscillation have some decrement in the amplitude, and that is what we call the logarithmic decrement. So, even we perform the experiment in the air also. That means, if the disc is oscillating in the air medium, still it is not going to continue the oscillations till infinite time. The oscillations will be died after some time, and yes, after each oscillation the amplitude is decreased. by whether a very small amount, but it is going to be decreased. So even in air, and obviously as compared to air, the liquid is having more resistive force, so obviously the decrement is going to be very fast in the liquid as compared to the air medium. So that is what we will find, right? Okay. So next is what we have some procedure. So what actually procedure I will tell you instead of reading these all things. So for your knowledge, we can just have a look on this particular part. So we have to do this experiment in little two parts. First of all, we have to take the logarithmic decrement, means we have to take the oscillations in the air medium, and then we have to dip that oscillating disk into the water, because we want to find the coefficient of viscosity of water. So what we will say, to have a little bit simplification, we have made two parts separately. First part is what, taking oscillations in air, right? So, and before that, taking oscillations in the air and all, before that we can find the time period t. So time period t we will find again. Obviously the time period has to be found in the air medium only. There is no any concern of the decrement to the time period. So we will find with the air medium, right? And from the time period only, we will get the moment of inertia I. And how it is? So you can see the formula. Then yes, what is that? Mean radius of the ring. Again we have to put one of the ring on the disc, and that ring's radius we will denote it by r dash. And first of all, we will find the moment of inertia of that ring which is kept on the disc. While doing the experiment part, we will understand what is ring and what is disc. And so first of all, we will find the moment of inertia of that disc ring. It is m dash square, right? I dash is equal to m r dash square, we know that is. And if we keep this time period, two time periods, right? So here without ring, whatever may be the time period, we will denote it by t, and with ring, whatever may be the time period, we will denote it as t dash, right? So these two time periods and this I dash, if we kept here, so we will get the I, and that is required for calculation of our final coefficient of viscosity. So first part we will do only for the time period. So without ring, we have to take the two trials of 20 oscillations, then take the mean and divide the mean by 20. So we will get the time period without ring. We have to follow the same procedure, but keeping the ring on the disc. Okay, so since the mass has been increased, because the ring is also having some mass, we know ring is having 415 gram mass, and that disc is having 1150 mass. So the mass has been increased, that means inertia has been increased, and therefore the time period required will be more. And therefore again with ring we have to take the two trials, then mean and divide it by 20. So we will get the time period with ring. So this is what one of the part. In the second part, we have to find the logarithmic decrement. Logarithmic decrement moreover in the air medium. So actually it is this experiment, we have to take the three observation tables. So we can say three parts. So first part only for the time period, we will get the time periods. Second part logarithmic decrement, but in the air medium. So in the air medium, what we have to do, just remove the ring on the disc, then take the oscillations, and at this time we have to measure the scale reading, not only the oscillations, we have to measure the scale reading. And yes, we have to measure the scale reading in this order: first reading, then after 20 oscillations just write down the 21th reading, then after 20 oscillations write down the 41th reading. So we will measure the scale reading after each 20 oscillations till 101, right? So you will understand that for the first reading and for the 21st reading, yes, there is a major decrement in the 21th reading as compared to 21th reading. 101th reading will be again more or less. That means the amplitude of the oscillation is going to be decrease, right? So we will note down here the scale reading, then we will take the log of that reading, and if we take the two successive difference, that means log of theta n minus log of theta n plus 60, right? Then this is what actually the logarithmic decrement, and the mean of this is what the mean logarithmic decrement, right? Actually this is mean decrement, and we will find from that lambda 0. So the lambda 0 will be 2.303, and that whatever may be the x we have calculated, that we will substitute here and divide by 60. So this is actually the log decrement in air medium, lambda 0. In the same way, we will keep now the oscillating disk in the water. We will keep the oscillating disk in the water medium, but we know the air the resistive force of the water is more, or the viscosity is more as compared to the air, and that's why what happens, that's why the oscillations are not going to be longer oscillation. That means we cannot go to the 101 as we have taken in the air medium. We have taken 101 oscillations, but in the liquid medium it is not possible. That's why we will take only the 11 oscillation, and we will note down the readings one after another. That means we will note down first, then we will skip the second oscillation, we will note down third, then fifth, 7, 9 and 11. In short, we can say we will just note down the readings of odd oscillations. Again same procedure, after note down, take the log of those all oscillating readings. Then if we take the difference like this, log of theta n minus log theta n plus 6, then whatever may be the mean, we will call it as mean y, and that mean if we substitute here, that is 2.303 log theta n minus log theta n plus 6, that is what actually y, this mean y, and it will divide by 6, then we will get the lambda, that is logarithmic decrement in liquid. This lambda 0 is logarithmic decrement in air, and this is in liquid. Okay, this is what the small what we can say the procedure to find the thickness of the polished disc. We know by using the screw gauge we can find that thickness very easily. And yes, these are some observations. The mass of the ring is 415 gram. Then radius of the ring we have to find, we will find it and then we will note down here. Radius of the disc we know it is r, thickness of the disc is d, density of the given liquid we know we are using water, that's why its density is 1 gram per centimeter cube. And yes, the logarithmic decrement purpose that we will find. And finally, what is T1 dash and what is T2 dash. So T dash or T dash and T. So T dash is what, the time period with ring, and T is what, without ring. And finally, by substituting all the values in the formula of eta, we will find the coefficient of viscosity, and which will be measured in the unit poise. So this is what just an what we can say one of the value, but don't take this as the granted value. That value we have to find, right? So after calculation, we will note down the final value of coefficient of viscosity, and that is measured in poise. Okay, right. So friends, now come to the experimental part of this experiment or this practical. So as you can see in the diagram, or as we have seen in this particular chart discussion, we have an oscillating disc. Yes, it is attached here, which is fixed here to this particular hanger. One end of the wire is fixed here, and to the other end we have a disc, we know that, and a small mirror is fixed on the oscillating disc, and this is what the lamp and scale arrangement. So a lamp is focused on this small mirror, and the spot or the reflection of this mirror will be seen as one of the spot on the scale. I hope you can see the spot on the scale, right? So what that actually helps us for to measure the swing as well as to measure the number of oscillation also, because when a disc is rotating, it is a little bit complicated to measure the oscillations. That means from where we have to start and from where we have to stop. That means we have to face some problems to consider the origin, to consider the reference point. But as you can see, the spot is a little bit oscillating. We have some little bit oscillations of this disc and the spot. So now if this spot is oscillating, or if this spot is moving on the scale, that means ultimately this is what actually the disc is oscillating. If that spot is moving from this point to this point and again come to the original point, then we can say one oscillation has been completed. So likewise we can count the oscillation. At the same time, you can see the scale is also printed on this particular white scale. Measuring scale is also printed, so that you can measure the scale reading. When we are going to the second and third part, then to calculate the logarithmic decrement in the air as well as in the water, we have to take down the scale reading, not only the oscillation, right. So, for the first part we know we just have to measure the time for 20 oscillations, right. So, for that purpose what we have to do, we have to just set this disc into the oscillations. Right now the spot is moving little bit, but not very well oscillations, so that we can count. So, what we have to do, you just have to set the disc into the oscillation. Now, I hope you can see the spot which is moving on the scale, and yes, at the same time you have to keep in mind that that spot should not go out of the scale, so that you can measure it only. Now, 0, right. Now, it went to the other extreme position and comes to the original 1 oscillation. Likewise, again it goes to there, it comes here 2 oscillations, it went to the other extreme position, then mean position, then this position, 3 oscillations. Likewise, how many oscillations you have to count? We have to count 20 oscillations, and at the same time when you said 0, you have to start the stopwatch. So, the stopwatch has been started and the oscillation count is also started. So, once the 20 oscillations has been completed, you have to stop the counting of stopwatch, note down the time. That is what your first trial, that is time required for 20 oscillations. If the oscillations are still going, then you can count for the second trial with the same oscillation also. But if you feel no, the disc should oscillate more with more amplitude, then you have to set once again into the oscillation. And at the same time you have to keep in mind the disc should not have oscillations in vertical plane, it should be oscillate in the horizontal plane only, right. So, as the spot is moving very neatly to the right and left side, you can understood that yes, the disc is taking only the horizontal oscillation. If the spot is taking some fluctuations in vertical direction, then you should stop the disc and again set it into the horizontal oscillations only. Okay, right. Now, you can start the second trial from this point also. Now, let us say 0, it went to other side, comes to the same point, then 1, then 2, now it is 1, then it comes, then 2, and so on. So, take the 2 trials, take the mean and divide the mean by 20. So, what we will get is the time period capital T. Now, here we have taken the time period without ring. We have taken the time period without ring. Now we have to increase its inertia, we have to increase its mass, that means we have to keep the ring. Now, this is what the 2 halves of the ring. So, what we can say, if we joint them, so this looks like a ring. So, we have to keep this ring on that particular disc. So, how to keep? We have 2 small notches on the middle of these 2 halves, and we have 2 small holes on the disc also at the same point. So, we can keep the disc on the we can keep the ring on the disc very perfectly in that particular holes, so that the disc will be little bit heavier as compared to the previous mass, right. Now, previously only disc is oscillating and the mass of the disc we know it is 1150 gram, but now we have mounted a ring on the disc. So, the weight of the ring or the mass of the ring also 450 gram. So, obviously the mass has been increased almost by 450 gram or 400 grams. So, therefore, again we have to note down the time period only with the ring. So, if it is in the oscillation mode, then no problem. Okay, right. So, the disc is taking oscillations now, and yes, the with ring. So, again we have to count. So, it is now it's 0. We will start here. Okay, but I have not started the stopwatch. So, once again 0. Yes, now the stopwatch is also started. So, we have to measure the 20 oscillations. Now, it is 1, right. Now, it will come to the other go to the other side, it will come to the same position, then 2, and likewise, and as the 20 oscillations will completed, we will stop the stopwatch, note down the time. Again we have to take the 2 trials with the ring, as we have done for the without ring, similarly we have to do for the with ring also, right. Once you completed these 2 time period part, that means T and T dash you will get after dividing the mean time by 20, right. We will get the time period T and T dash. Now, next just remove this ring again from the disc. We will keep this ring aside. Again we have to find the radius of the ring also. So, how to find the radius of the ring? So, this is the ring. To find its radius, first of all take a string and measure its circumference, and from that circumference you can find the radius of the ring. Once it is done, then keep aside. Now similarly we have to find the radius of the disc also. Take a string, yes, knot it around it and measure the distance, that will be the circumference, and from that we can find the radius of the disc. It is denoted by r and radius of the ring is denoted by r dash or r prime. Now next what we have to see is the logarithmic decrement, our third part or our third observation table, right. For the third observation table, again the disc is already set into the oscillation, but yes, the oscillations are out of the scale and that is what we do not want. So keep the oscillation or the spot should play on the scale only. So that is what we have to keep in mind, that we should maintain, so that because now onwards not only we have to measure the oscillation, but at the same time we have to note down the scale reading also, either this side or that side. Now I will call it as theta 1, so it is its reading is 15. Now just count it, 2, then 3, 4. Now next we have to measure the reading of only theta 21, means if 21 oscillations are completed, then only we have to note down the reading. Then again 22, 23, 24 we have to count the next oscillations, measure the 41th oscillation. Similarly 42, 43, 44 and we have to measure the 61th oscillation, then 81th and 101th. This is what the procedure, what we have to note down, scale reading. Okay, that means for the first oscillation it is if it is 15, it was 15, then for the 101 oscillation it is something 5 or 6. That means yes, the decrement has been takes place. That means the oscillation amplitude is decreasing, and that is what we call the logarithmic decrement. So this happens in the year. So that is what our lambda 0, that means we will find the logarithmic decrement in year, that is lambda 0. Next one is what, logarithmic decrement, that means we have to follow the same procedure. We have to count the oscillation, at the same time we have to note down the scale reading also, but we have to keep this disc in the water or the liquid of which we have to find the coefficient of viscosity. So here we are using the water liquid, and yes, its coefficient of viscosity we have to find. So we have to keep the disc in the water, and yes, at the same time disc should oscillate, but we know that the water will have more viscosity as compared to air or more resistive force. Therefore the oscillations will not have that much amplitude. At the same time the decrement will be fast, and therefore we will not count 101 oscillations, we will count only 11 oscillations, and we will skip the even numbered oscillations, we will just count or note down the odd number oscillations, right. So how to keep it into the, now this stopwatch is not required for us, we just have to keep this particular disc into the water. So here I have kept taken water in this pot, so I will try to dip this particular disc into the water and make it oscillate also. So it is not sufficient, so one more we will keep, so that the disc will be completely dipped into the water. Yeah, now it is okay, right. And yes, the disc should not touch to the pot also. So yes, that is what we have to do. Now again count the 11 oscillations, and yes, note down the readings of corresponding even, not even, only odd number. That means if first oscillation is start from 20, then count the second one, but don't write reading, then write the reading of third one, then skip the fourth one, then write the reading of fifth one, and so on. We have to do till 11th oscillations, and from that we will get the logarithmic decrement in water medium. Now the disc is dipped into the water medium, okay. And then yes, obviously we have to find the disc's thickness also, thickness of the polished disc. So obviously we have here a screw gauge, so by using this screw gauge we can find the thickness of the disc. So I am just making the gap and attach it to the disc. Yes, we know that, and for the accuracy purpose what we will do, we will take the 3 different readings. So, this is what note down the main scale reading, then circular scale reading, and multiply the circular scale reading by least count, take the first reading at this point, then second reading at this point, and third reading at some other point, and we will get the accurate disc thickness, right. So, all the things are known to us, we have to substitute in the formulas and we just have to find the coefficient of viscosity. Let us come to the calculation part, right, how to note down the readings. So, that is what we have done here. So, the first part we know it is for measurement of the time period only. So, what we will do, we will keep the ring on the disc, or first of all without ring. So, only disc we have to oscillate and we have to count the 20 oscillations. So, for first trial it will take 123 seconds, for second trial it is taking 133. So, these numbers may be different for different users. So, this is just an example we can say, and we have taken the mean of these two readings. So, and after dividing these mean seconds by 20, so we will get the time period, right, and this time period we know it is in second, time period 6.4 seconds without ring. But as I told, as soon as we kept the reading, the oscillations means inertia has been increased because due to the mass has been increased, and it will take more time. So, take the two reading, trials, again take the mean, and after dividing 20, what we will get, it is 8.75. So, yes, this is T and this is T dash, right. Once you got the T and T dash, then we can find the I, but first of all we will take the second part observation table also. So, in the second part what actually we have to find, we have to find the logarithmic decrement in the year. So, what I am saying is that since once you have noted down the reading for the first swing, we can say first swing or first oscillation. So, the scale reading is 23, then just count the 20 oscillations, do not write the reading, just count the 20 oscillations, and after the 20 oscillation again note down the reading of 21th oscillation, again count 22, 23, 24 up to 40 oscillation, and finally write down the reading of 41th oscillation, right. Again count 42, 43, 45 and so on, count up to 60, do not write the reading, and write down the reading of 61st, right, 61th oscillation and so on. So, finally, we have to write down the reading of 101th oscillation. Now, you can see as the swings has been increased, the reading is going to be decreased, that means the damping has been taken place, and that is what we have to exactly found. Now, take the log of this all reading, corresponding reading, taking log, and then now taking the difference, corresponding difference we can say. Now, see log of theta n minus log theta n plus 60, theta n plus 60, log of theta n plus 60. So, what is that? If we substitute, what is the value of n first? 1. So, log theta 1 means this, log theta 1 minus log theta n plus 60 means 1 plus 60, 61. So, what is the log theta 61? This is this value 61, right. So, this is what we have taken the difference of these two. So, this will have named x1. Similarly, now what is the next value of n? It is 21. So, log 21, that means this value log 21 minus log 21 plus 60, it is 81. So, here is 81, this one. So, again the difference of these two. So, we have named it as x2, and finally, what is value of n? Third one, because we have 6 readings, then how many differences we will have? Only 3 differences. So, 2 has been over. Third difference 41, log 41, this value log 41 minus log 41 plus 60, 101. So, the difference of this is this one, and then the mean of these 3 values. So, this is what the log theta n minus log theta n plus 60. Okay. Again here the mass of the ring is, I told you, 415 gram. Then radius of the ring, just take a string, and take its circumference, then we will get the 2 pi r is equal to circumference, 2 pi r is equal to circumference, and whatever maybe it is in centimeter. So, from that we can find the r value. Then the radius of the disc. So, disc and ring are almost same, but yes, we will find separately, and the thickness of the disc after calculation by using the screw gauge we will get 1.14 centimeter, and the density, yes, gram per centimeter cube of our liquid. Which liquid we are using? Water. So its density will be 1. So these are the observations. Now once we got this mean value, we have to substitute in the formula of lambda 0, right? So the lambda 0 will be here. So substitute the value of mean in here. So 2.303 divided multiplied by that bracketed value, that mean value, divided by 60, and this is what the value of lambda 0. This is actually the logarithmic decrement in air medium. Okay. Now for the second, this is now in liquid. Moreover, which liquid we are using? Water. Logarithmic decrement in water. So again same we have to do for the first oscillation. Note down the reading, then skip the second oscillation, but note down the reading of third, then skip the fourth, write down the fifth, and so on until 11th oscillation or 11th swing. So again we will find here also the decrement is little bit faster because of the liquid resistivity, or we can say the viscosity. And again we will take the log of these all corresponding readings, taking log, and again we will follow the same procedure, log theta n minus log theta n plus 6. Earlier it was 60 because we have more oscillations, but here only 11 oscillations, that why we will take the 6, right? Again here 1 plus 6 means 7. So the difference of first and 7th, we can say these two, this is y1. If we keep the n is equal to 3, so log theta 3 minus 3 plus 6, 9. So 3 and 9. So this is 9, this one is 3. So 3 and 9. And finally n is equal to 5. So log theta 5 minus log 5 plus 6, 11. So log theta 5 and 11. So this is x3, or sorry we can say y. For the air medium we have noted it for x. So again the mean of these three, y1, y2, y3, this will be the 0.3233. And if we substitute this value here in this bracket, here not it is 6, it is only 60, it is 6, theta n plus 6, and we will divide it by 6. So this is what the logarithmic decrement in the liquid, logarithmic decrement in the liquid. If we substitute this value here, so we will get the logarithmic decrement in the liquid. Okay. So these are what the calculations by log table, nothing else. Now what we will do, we got lambda 0 and almost all the observations. How we have found the observations? Yes, the calculation part is here. For the ring, for the disc radius, just taken the circumference, and the circumference is found to be 40 centimeter, and we have equated that to the 2 pi r, and yes, we found the radius, it is r is equal to 6.369. Okay. Now radius of the ring, for the ring also we will keep the same procedure to find the radius. What we will do is again find the circumference, and its circumference is found to be 39 centimeter, and from that we got the radius of the ring is 6.21. Now once you got the radius of the ring and the mass of the ring is known to us, 450 gram, just substitute the in the moment of inertia formula and get the moment of inertia of the ring. So this is what the moment of inertia I dash of the ring. Now once we got the I dash, let's go to the I to find the I. So to find I, we have this formula, t square divided by t dash square minus t square into I dash. So t and t dash already found in the very first observation table, and I dash is found here. So substitute all the values and get the value of I. Once you got the I value, right? Yes, this is what the I value. So once you got the I value, it is 18,410 gram centimeter square. Now everything is found in this formula, right? Everything is with us, and now you can move towards the finding coefficient of viscosity. So let us keep the all values. 16 I value, this is I value, pi 3.14, rho density 1, t already known to us, both the radiuses we have found. Actually it is radius of only disc, and the thickness of the disc is also found, it is 1.14. So all values we will keep and do the calculation very carefully, and after doing the calculation, so finally what we will get is the coefficient of viscosity. So the calculations are little bit complicated or little bit lengthy, we can say, but yes, finally we will find some final value, and that will be the coefficient of viscosity. Coefficient of viscosity of given liquid, but now here we are using the liquid as water. So this is what the coefficient of viscosity of water. Maybe it is not the standard value, but yes, whatever we found that we should write, and maybe some errors due to the purity and all these things. And finally we have to write the result as coefficient of viscosity of water is found to be, whatever may be your answer, you have to write in the unit points. Okay. Yes friends, this is all about the practical coefficient of viscosity. Okay, so yes, this is what the simple method to find the coefficient of viscosity of any liquid. Instead of water you can use other liquid also. You can find the viscosity of oil or edible oil or your castor oil and all, right? So yes, this is what the efforts to make this practical successful. And if you feel this is value addition, like the video and share with your friends, subscribe to our channel, and yes, press the bell icon so that you will get the notifications of our next video. Thank you so much for watching.